Okay, this time we have a curve which is enclosing a circle. Because it's enclosing a circle, it's a straight up application of the Green's theorem. It doesn't say verify. So we can just say, oh, this is equal to the other one, and therefore we can use this one to calculate this one. And that's how I want to solve this. However, there's a catch, because this curve, if you draw it, it starts at t equal to 0. It starts at 0, 4. And if you look at the derivative of this, it's 4 cosine t, negative 4 sine t. And if you plug in 0 here, you end up with 4, 0. So the velocity vector at this initial point is this vector, 4, 0, which means that the curve is going clockwise. Why is that a problem? Clockwise, why is that a problem?
Going the opposite way.
Because this says it should be counterclockwise, and this is clockwise. And therefore, in order to apply this, what should you do? you have to use the fact that if you do clockwise, then this is negative of the counterclockwise, and therefore you should be using negative of the double integral. Okay? So that's what you have to do. So you have to calculate this, and at the end of the day, you have to apply a negative sign to get the correct answer. If you forget to apply this negative sign, you're going to end up with the wrong answer off by a negative sign. Okay? All right, so let's try it. Apply the curl, two-dimensional curl is this with the two functions written. Now, by the way, if you try to do this calculation directly by dividing by dt and multiplying by dt, that means you have to plug in 4 sine t into this x, and you end up with sine of sine squared of t. I don't know how to integrate that. It's going to be a very tough integration to do. Okay? So, I mean, just having this Green's theorem is a tremendous value in this case. You're able to answer some integral in a completely different way, where direct method is actually practically impossible. All right, so let's compute this. You're supposed to do this. That's how you do determinants, AD minus BC, which is round x applies to that. What do you get if this applies here? Negative 3, because this is a partial with respect to x. Any y is considered as a constant, so although this is very complicated, in the eyes of the partial derivative, it's just a constant, and therefore its derivative is 0. So you only have to differentiate negative 3x, which is just negative 3. Minus, what happens when round y hits this one? This one is 0, because, again, partial with respect to y, we think of x as a constant, so that's 0. Partial with respect to y hitting negative 7y gives you negative 7. So you end up with negative 3 minus negative 7, which is 4. Okay? Now what? Now you have this right side. What's the integral? Over this circle of, by the way, what's the radius of this circle? 4. 4. This is 4, because it's 0, 4. So you have integral of 4dA of this circle, and if you pull this 4 outside, you end up with integral of 1dA over the circle. If you integrate 1 over some domain, what do you get?
The area.
You get the area, right? So you have to do 4 times the area of the circle, which is pi r squared, and our radius is 4. 4 squared is 16. 16 times 4 is?
64.
64. So you have 64 pi. Is this the answer?
No.
No, what do you have to do? You have to negate it, because the orientation is the opposite. So the answer is negative 64 pi. You have a question? Yes.
When you're doing it, can you just write, like, just for your own sake, like negative double integral 4dA? Like, is that acceptable?
Yeah, you can do that. You can say, I mean, here's another way to write it. You can say, if you do negative of double integral and then say it's equal to this. So you can start from here. You can say
Okay.
this, because it's clockwise, it should be negative of this. You put a negative, and so on and so on. That's another way to do it.